Hello and welcome to the next lecture in the subject State Space Approach to Control System Analysis and Design. Today we are going to discuss the topic Equivalent State Space Models based on Similarity Transformations. So in the last lecture we have seen when we were discussing the conversion of transfer functions into state space models, then we saw that we can get from the transfer functions mathematical models which are either in the diagonal or in Jordan or in companion forms, various canonical forms. So before we come to that, we will first discuss how from a given state space model of a system we can obtain another model based on the similarity transformations. Generally, when we do the mathematical modeling, we choose the physical variables of the system as its state variables. For example, when we were discussing the electrical circuit, series circuit consisting of R, L and C components, we choose the charge flow as the state. So that's not necessary. We can take other variables as the state variables, and this is what is to be done today. So many choices of state variables are possible, and each choice of state variables will lead to a different representation, meaning that system matrix and input matrix in one representation will be different from the system matrix and input matrix in the other representation. However, one form of representation may be preferable to the other form for convenience of either the interpretation or the analysis. For example, we will see subsequently that when the system description is available in diagonal form or the Jordan form, solving the state equations becomes very easy. Similarly, when the representation is available in the companion form, then design of control or observers becomes very easy. Now we come to how to transform the system from one representation to the other representation using the similarity transformation. So we begin with the state space model, which is shown here. So this one, x dot equal to ax plus bu, y equal to cs, a being the system matrix, b the input matrix, and c the output matrix. The state variables here are x, which is set of quantities x1, x2, etc. up to xn. These n quantities, meaning that the system order is n. So we want to represent it into another form where the state is z and not x. However, it also consists of n variables z1, z2, etc. up to zn. That is necessary. And we postulate that these new state variables z are related to x through a similarity transformation T, a transformation matrix which is non-singular. Through that it is related x equal to tz. That is the relation. So to obtain the equivalent model, what we do is, in the state equation which is given to us, x dot equal to ax plus bu, we substitute this relation x equal to tz everywhere in place of x. So what we get, x dot becomes tz dot because t is constant matrix. So x dot will be tz dot. And ax becomes a tz. And of course bu remains as it is. So what we do is we pre-multiply all the terms by T inverse, both on the left side as well as on the right side. So what we get, we multiply this one with T inverse. So T inverse T gives an identity matrix. So that gives Z alone on the left hand side. On the right hand side, this T inverse AT, which is here, and T inverse B, which is here. And we denote this T inverse AT as A bar, this T inverse B as B bar. So this becomes Z dot equal to A bar Z plus B bar U. Similarly, in the output equation, we substitute in place of X that TZ, this one. So we get Y equal to C TZ, and we denote this CT by C bar. So we get Y equal to C bar Z. So in the new representation, this system matrix is A bar, the input matrix is B bar, and the output matrix is C bar. The state is Z. In the original representation, the state is X. Matrices are respectively A, B, and C. And we have seen that A bar is related to A like this, B bar is related to B like this, and C bar is related to C like this. So this model is equivalent to this model. Both are of order n. Please remember that X consists of n quantities, also Z consists of n quantities. As an example, we consider this system. Here X dot is this matrix, which is a diagonal matrix. This is the system matrix A, and this is the input matrix B. And Y is, this is the C matrix 1 1 X. Now we want to transform to a new representation where the state variable will be Z related like this, X equal to TZ, and in that we are going to select T as this. You can check that its inverse will be this. T inverse will be 1 1 minus 1 minus 2. So we can pre-multiply and post-multiply the matrix A respectively by T inverse and A to obtain A bar, and then we will get this. Similarly, we pre-multiply B by T inverse to obtain B bar, and we get this, and C we post-multiply to get C bar, and this will be this. So the system equation which was given as this one will change to the one given by this one. This will become the system matrix in the new representation. This will become the input matrix in the new representation, and this becomes the output matrix in the new representation. A bar, B bar, and C bar, as they were introduced in the previous slides. Now, there are certain properties which similarity transformations or equivalent state space models they satisfy, they have. So these are that the original system and the transformed system have the same characteristic equation. The system matrix in the original representation and the system matrix in the transformed representation, in the equivalent representation, have the same characteristic equation, and also the two systems have the same transfer function. This is what happens. Now we will prove one by one both of them, and first we are going to prove that they have the same characteristic equation. So we start with the characteristic equation of the original system, which is determinant of Si minus A equal to 0. This is the characteristic equation of the original system, X dot equal to Ax plus B. Now in this what we do is we substitute in place of A in terms of A bar. So we knew that A bar is T inverse AT, meaning that A will be T A bar T inverse. So we do this substitution in place of A, and also in place of identity matrix I, we substitute T inverse. Okay. And so of course T inverse and T inverse are identical, so we substitute I by T inverse. Then we take out T on the left and we take T inverse common on the right. So we get this one becomes like this, that T Si minus A bar into T inverse, the determinant of whole thing will be 0. And because the determinant of product of matrices is same as the product of determinant of matrices, so we get this whole determinant becomes equal to product of three determinants. One is product of determinant of T to the product of Si minus A bar to T inverse. And because the determinants are scalar quantities, so the determinant of T and determinant of T inverse, they multiplied to each other lead to unity 1, and so we are left with this thing becomes equal to Si minus A bar equal to 0. So the determinant Si equal to 0, this characteristic equation leads us to Si minus A bar, that determinant equal to 0, the characteristic equation of the transformed system, this one. We saw starting from the equivalent system, Si minus A bar equal to 0, the characteristic equation of the equivalent system, and to that we do similar operations as we did with Si minus A. So here also in place of I, we substitute T inverse IT, and in place of A bar, we substitute T inverse AT, and we do manipulations as before, so we obtain the characteristic equation of the original system. And this proves the first point, that the equivalent models have the same characteristic equation. Now to prove the other thing, that the original system and the transformed system, they have both the same transfer function, we do some mathematical manipulations like this. We start with the transfer function of the transformed system. In one of the earlier lectures, when I introduced transfer function, we derived that transfer function of a system GS is the output matrix C Si minus A inverse B plus D. Here we have not considered D, so we have the transfer function GS as C Si minus A, the inverse of that, into B. And because we are talking about the transformed system where the system matrix is A bar, input matrix is B bar, output matrix is C bar, we have the transfer function of the transformed system G bar as given by this expression. Now in this, what we do is in place of C bar, we substitute CT, which was derived in one of the previous slides. In place of B bar, we substitute T inverse B, and in place of A bar, T inverse AT to get this expression. Now what we do, we take T and this up to T inverse together like this. And then what we do is that we note that this is a product of this matrix T, this matrix, and this matrix. So the product of three matrices can be written as inverse of the product of the matrices taken in the last one first one last, and this one here. So what we do is this T inverse comes here as T, this T goes here as T inverse, and this one comes here and the inverse goes outside. This inverse, and this is inverse of T inverse that goes outside. So this we get this one, and then this leads to this one Si minus A, because T multiplied with Si is STI and T inverse multiplied to that Si T inverse, So that cancels and we are left with Si. T inverse AT, this T multiplies to T inverse, leaving identity matrix. This T multiplies to this T inverse, leaving again an identity matrix. So what remains is essentially the A. So Si minus A, the whole inverse, B, this C. This is the transfer function of the original system, which we wanted to show, that has been shown. Now we summarize this lecture. Choice of state variables of a system is not unique. Hence, state space representation of system is also not unique. Depending upon what state variables we choose, we obtain different models. And we can also select similarity transformation, a non-singular transformation matrix T, and through that, as we saw in the initial portion of this lecture, we can always obtain different state space representation if we have different transformation matrices. However, this is something which we have to remember, that all the equivalent models obtained through different similarity transformations will have the same characteristic equation as well as the same transfer function, meaning that the input-output relationship of a system is preserved. That doesn't change. That completes our this lecture. See you again in the next lecture.